There are several common types of refrigeration systems in use today, and they all accomplish the same basic task. They remove heat from an area or substance and keep it cool. In this part, we'll look at how a typical vapor compression refrigeration system works. We'll use some approximate temperatures and pressures as we trace the flow of refrigerant through the system. Here is a simplified illustration of a typical vapor compression system. The main components are an evaporator, a compressor, a condenser, a receiver, and an expansion valve. When the expansion valve is open, it allows the liquid refrigerant to expand into an area of low pressure. The refrigerant that leaves the valve is in the form of a liquid vapor mixture. This expansion causes the pressure and temperature of the refrigerant to drop. In this system, the refrigerant that leaves the expansion valve is at a temperature of about 5 degrees Fahrenheit and a pressure of about 25 psia. Next, the refrigerant enters the evaporator, where it absorbs heat from the evaporator's surroundings and changes completely to a vapor. As the refrigerant absorbs heat, it cools the evaporator's surroundings. Because of the temperature difference, heat continues to transfer to the refrigerant. As a result, the temperature and pressure of the refrigerant increase slightly. From the evaporator, the refrigerant is drawn into a reciprocating compressor. The compressor increases the temperature as well as the pressure of the refrigerant. The refrigerant is forced out of the compressor at about 125 degrees Fahrenheit and 180 psia and sends it on to the condenser. The condenser is a shell and tube heat exchanger that uses water flowing through the tubes as a cooling medium. The water removes heat from the refrigerant, and the refrigerant becomes a liquid again. The refrigerant flows next into the receiver. Here the refrigerant is at a temperature of about 100 degrees Fahrenheit and a pressure of about 130 psia. From the receiver, the refrigerant flows back to the expansion valve and the cycle continues. Absorption refrigeration systems use chemicals called absorbents to control the pressure and temperature inside the system. A common application of a typical absorption refrigeration system is to cool water. The cooled or chilled water is then pumped to various components where it absorbs heat. We can look at an illustration of an absorption refrigeration system to see how it works. The example system consists of 4 main sections: an evaporator, an absorber, a generator, and a condenser. To see how this system works, let's start with the evaporator section. The water to be cooled or chilled water flows through tubes in the evaporator section. Refrigerant, which is also water, is pumped from the bottom of the evaporator and sprayed onto the tubes. As the heat transfers to the refrigerant, the chilled water cools and some of the refrigerant vaporizes. Any refrigerant that does not vaporize collects at the bottom of the evaporator. The temperature of the chilled water is typically too low to vaporize the refrigerant at atmospheric pressure. This system operates at a very low pressure to allow the refrigerant to vaporize at low temperatures. In our example, the pressure is around 0.15 psia. At this pressure, the refrigerant will vaporize at 45 degrees Fahrenheit. The low pressure that's needed is achieved by using a chemical absorbent such as lithium bromide. The refrigerant vapor from the evaporator flows into the absorber section, where a relatively hot lithium bromide solution is sprayed into the vapor. The lithium bromide absorbs the vapor, and a mixture of absorbent and refrigerant is formed. When the lithium bromide absorbs the vapor, the volume of the vapor is greatly reduced, which causes the low pressure. The lithium bromide and the refrigerant will be reused in the system, but to do this, they must be separated. The separation takes place in the generator section, which means that the mixture, called weak absorbent, must be pumped to the generator. However, the weak absorbent is hot enough to boil inside a pump, so it must be cooled first. The cooling takes place in the absorber. Cooling water passes through tubes inside the absorber and cools the weak absorbent flowing around the tubes. From the absorber, the cooled weak absorbent is pumped into the generator section. In the generator, the weak absorbent is heated by steam passing through tubes. When the weak absorbent is heated, the refrigerant boils off, leaving the lithium bromide behind. This lithium bromide is called strong absorbent, since it has a strong ability to absorb refrigerant. The refrigerant that boils off in the generator is sent to the condenser. We'll see what happens there in a minute. The strong absorbent is sent back to the absorber. On its way, it passes through a shell and tube heat exchanger. Weak absorbent on its way to the generator also passes through this heat exchanger. In this heat exchanger, the strong absorbent gives up some of its heat to the weak absorbent. Cooling the strong absorbent increases its ability to absorb the refrigerant vapor when it's sent to the absorber. This helps to maintain the low pressure in the unit. Heating the weak absorbent increases its temperature, so less steam is needed in the generator to separate the refrigerant from the absorbent. This makes the system more efficient. Meanwhile, in the condenser section, the refrigerant vapor flows around tubes and is cooled by cooling water passing through the tubes. As the refrigerant gives up heat, it condenses and forms a liquid that collects in the bottom of the condenser. The liquid refrigerant in the bottom of the condenser drains into the evaporator. In the evaporator, the refrigerant from the condenser mixes with the refrigerant that is already there, and the cycle begins again. In this topic, we looked at the operation of a typical vapor compression refrigeration system and at the operation of a typical absorption refrigeration system. Take a moment to try some practice questions on this material. Next, the refrigerant enters the evaporator, where it absorbs heat from the evaporator's surroundings and changes completely to a vapor. As the refrigerant absorbs heat, it cools the evaporator's surroundings. The low pressure in the system is achieved by using a chemical absorbent such as lithium bromide. The refrigerant vapor from the evaporator flows into the absorber section, where a relatively hot lithium bromide solution is sprayed into the vapor. The lithium bromide absorbs the vapor, and a mixture of absorbent and refrigerant is formed. When the lithium bromide absorbs the vapor, the volume of the vapor is greatly reduced, which causes the low pressure. A refrigeration system lowers the temperature of a substance or an area. The controls used with a particular system depend on the system and how the system is used. To operate properly, a refrigeration system must control refrigerant pressure and flow. In a system that has a reciprocating compressor, the flow of refrigerant is produced by the pressure exerted on the refrigerant in the compressor. Some types of refrigeration systems maintain the desired amount of cooling by cycling the compressor on and off. This controls the amount of refrigerant that flows to the evaporator. In many systems, refrigerant flow, and therefore the amount of cooling, is controlled by an expansion valve. The position of the expansion valve is controlled by the temperature of the substance being cooled. Some control systems use a thermostat located in the area being cooled to position the expansion valve. Other systems may use a thermal bulb or a thermocouple. We'll use an expansion valve and a thermal bulb to see one way to control the amount of cooling that a refrigeration system provides. This illustration shows the expansion valve, the thermal bulb, and connecting tubing. A metal bellows inside the expansion valve is connected to tubing that leads to the thermal bulb. The thermal bulb, tubing, and bellows contain a fluid that expands when it's heated and contracts when it's cooled. The thermal bulb is mounted on the refrigerant line between the evaporator and the compressor. It senses the temperature of the refrigerant leaving the evaporator. The temperature of the refrigerant is proportional to the temperature of the substance being cooled. For example, if the temperature of the substance increases, the refrigerant's temperature increases as well. So if the temperature of the substance being cooled is above its desired value, the temperature of the refrigerant will also be higher. Heat in the refrigerant will transfer to the thermal bulb, and the fluid in the bulb will expand. This expansion forces fluid into the metal bellows. What do you think happens to the metal bellows? The fluid causes the bellows to expand and open the valve more. This allows more refrigerant to flow through the expansion valve. In the evaporator, the additional refrigerant removes more heat from the substance, and its temperature decreases. If the temperature of the substance being cooled goes below the desired value, the temperature of the refrigerant leaving the evaporator will decrease. In this case, the refrigerant absorbs heat from the fluid in the thermal bulb, and the fluid contracts. This causes the expansion valve to close slightly and reduce the flow of refrigerant to the evaporator. Now that we've seen how flow is controlled, let's see how a system maintains pressure. As you may recall, the pressure exerted on the refrigerant in the compressor creates the flow through the system. Let's look at a refrigeration system that uses pressure switches to help maintain the proper pressures in the system. This system has a low-pressure cutout switch located on the compressor suction. It also has a high-pressure cutout switch on the compressor discharge. When the system is operating and the temperature of the substance being cooled drops, the temperature and pressure of the refrigerant entering the compressor will also be lower. If they get too low, some of the refrigerant will not vaporize and will remain as a liquid. If liquid refrigerant is allowed to enter the compressor could be damaged. So when the pressure of the refrigerant decreases below the set point for the low-pressure cutout switch, the switch shuts off the compressor. Refrigerant continues to flow through the evaporator and absorb heat. More refrigerant vaporizes and the refrigerant pressure increases. When the pressure rises above the set point of the low-pressure cutout switch, the compressor will automatically restart. The high-pressure cutout switch prevents the compressor from overpressurizing the system. In systems with centrifugal compressors, the compressor runs continuously, and there may be additional components to maintain the desired values. For example, in this system, a bypass line routes some of the refrigerant around part of the condenser, the receiver, and the expansion valve. When this is done, the refrigerant that flows into the evaporator is warmer. The flow of refrigerant through the bypass line is controlled by a control valve to maintain the temperature around the evaporator. If the temperature around the evaporator gets too low, the temperature of the refrigerant flowing to the compressor will drop. When the temperature of the refrigerant flowing to the compressor drops, a temperature sensor sends a signal to a controller, which in turn sends a signal to the bypass line control valve, causing it to open slightly. This allows some of the refrigerant from the discharge of the compressor to be routed to the evaporator. This warmer refrigerant mixes with the refrigerant leaving the expansion valve and increases its temperature. As a result, less heat is removed from the substance being cooled, and its temperature increases back to the desired value. Another way that refrigerant flow can be controlled in refrigeration systems that have centrifugal compressors is by using dampers or vanes. These devices are often located in the compressor suction line. When the temperature of the substance being cooled is too low, the temperature of the refrigerant flowing to the compressor drops. The dropping temperature is sensed by a temperature sensor, which sends a signal to close the vanes slightly. This reduces the amount of refrigerant that enters the compressor, so the flow of refrigerant decreases. The reduction in flow will cause the refrigerant in the evaporator to be warmer. This causes the temperature of the substance around the evaporator to increase back to its desired value. Now, these controls are not the only ones you may find on a refrigeration system. For example, in some systems, a temperature instrument measures the temperature of the refrigerant and sends a signal to control the flow of water or air through the condenser. This, in turn, controls the amount of heat rejected from the system. This is another type of control system found on refrigeration systems with centrifugal compressors. This system measures refrigerant temperature and sends a signal to the controls of the compressor. This signal, in turn, controls the compressor's speed to maintain the desired amount of cooling. A vapor compression refrigeration system may have many indicators to help operators monitor and control the system. These indicators are often located on a panel so that operators can check the operation of the system from a single location. Operators routinely check the temperature indicators associated with a refrigeration system. In most cases, there are temperature indicators for the substance being cooled and for the discharge of the compressor. The condenser and the evaporator may also have temperature indicators located on their inlets and outlets. These indicators can be checked to see if heat transfer is taking place properly. Besides temperature indicators, there are also pressure indicators that should be checked. Two common locations for pressure indicators are the suction and the discharge of the compressor. Operators can use these indicators to monitor compressor operation. Some compressors have a lubrication system that uses an oil pump. The discharge pressure of the oil pump should also be checked. The correct discharge pressure indicates that the compressor's bearings are properly lubricated with oil. There are also level indicators that should be checked. Two common locations for level indicators are on the receiver and on the oil reservoir for the compressor's lubrication system. The level indicator on the receiver monitors the amount of refrigerant in the system. The proper level of refrigerant must be maintained in the receiver to ensure that an adequate supply is available. The level indicator on the compressor's oil reservoir is checked to see if the compressor has enough oil for proper lubrication. If the oil level drops too low, bearings and other moving parts may be damaged. Now, there may be other indicators you should check to ensure that a system is operating properly. For example, sight glasses on the receiver outlet can be used to check the flow of refrigerant. Ideally, a vapor compression refrigeration system will run efficiently and practically by itself. Sometimes, however, problems may occur. One of the more common problems that can affect a refrigeration system is an improper amount of refrigerant. The amount of refrigerant can be determined by checking a level indicator on the receiver or by checking a sight glass on the receiver outlet. When the amount of refrigerant in the system is correct, the refrigerant seen in the sight glass should be clear. If there's not enough refrigerant, the refrigerant may appear cloudy and it may contain bubbles. Another indication of too little refrigerant may be a continuously operating compressor. Some types of refrigeration systems cycle the compressor on and off to maintain the proper cooling. If this type of system has too little refrigerant, the compressor may run continuously, trying to maintain the desired amount of cooling. A similar problem is low refrigerant flow. One place where this is a problem is in the evaporator. When refrigerant flow through the evaporator is too low, less heat will be removed from the substance being cooled. This will cause the temperature of the substance being cooled to increase. The compressor may also provide an indication of a low flow problem. In a system with a reciprocating compressor, reduced refrigerant flow causes the pressure in the evaporator to decrease, and the control system may shut down the compressor. When the compressor stops, the refrigerant begins to warm up and the pressure starts to rise, so the compressor quickly restarts. Then the pressure is reduced again and the compressor again shuts off. This on and off cycling or short cycling will continue as long as there is a low flow condition. One possible cause of reduced flow through the evaporator is a stuck expansion valve. Dirt or scale can obstruct the valve and prevent it from opening properly. The same result can occur if there is a blockage between the receiver and the expansion valve. The blockage acts like another expansion valve, so the refrigerant will be cooler downstream from the blockage. One way to check for a blockage is to feel the line for cold spots. Now, a refrigerant flow rate that is too high can also occur. If the expansion valve sticks too far open, there may be too much refrigerant in the evaporator. This could cause the evaporator pressure to increase. In systems that cycle the compressor on and off, the compressor could operate continuously. This is because pressure in the evaporator is higher than the set point for shutting off the compressor. Another problem that can occur is a reduced condensing rate in the condenser. This can increase the pressure on the discharge of the compressor. What do you think happens if the pressure gets too high? In many systems, when the compressor discharge pressure builds up, the high pressure switch will shut off the compressor. There are a number of reasons why discharge pressure can build up from a reduction in the condensing rate. For example, a blockage between the condenser and the receiver will back up the refrigerant. This reduces the amount of condensing that occurs and increases pressure. Another cause of a reduced condensing rate is a decrease in the flow of cooling water. For instance, a blockage in the cooling water system could reduce the flow of water through the condenser and reduce the amount of refrigerant that can be condensed. Other possible causes of cooling water flow problems include cooling water valves being out of position and cooling water pumps not operating properly. Air binding in the water side of the condenser or in the cooling water system could also reduce the condensing rate. Compressor malfunctions can cause problems in a refrigeration system. Typical causes of compressor problems include loose or broken parts, worn bearings, and inadequate lubrication. Overloading is another refrigeration system problem. Overloading occurs when the area or substance that's being cooled contains more heat than the refrigeration system can remove. In this situation, the compressor may operate continuously, but the desired temperature will not be reached. Another problem that you might encounter is icing on the evaporator. This can occur if the system cools a space to below 32 degrees Fahrenheit and the space contains moisture. Under these conditions, ice forms on the evaporator and acts as an insulator, reducing the efficiency of the system. In this topic, we looked at some of the basic controls and indicators that are found on many refrigeration systems. We examined some of the operating checks that should be made on a typical refrigeration system, and we looked at some problems that can occur in refrigeration systems. Now try some practice questions on refrigeration system operation. To operate properly, a refrigeration system must control refrigerant pressure and flow. In a system that has a reciprocating compressor, the flow of refrigerant is produced by the pressure exerted on the refrigerant in the compressor. Some types of refrigeration systems maintain the desired amount of cooling by cycling the compressor on and off. This controls the amount of refrigerant that flows to the evaporator. In many systems, refrigerant flow, and therefore the amount of cooling, is controlled by an expansion valve. The position of the expansion valve is controlled by the temperature of the substance being cooled. Some control systems use a thermostat located in the area being cooled to position the expansion valve. Other systems may use a thermal bulb or a thermocouple.
In this example, the operator notices a trend developing on the moving X-bar chart. The plotted values are moving toward the lower control limit. The moving R chart appears normal. Even though the moving R chart appears normal, the pattern on the moving X-bar chart indicates that the process is unstable.
Reactions that produce heat after they're started are called exothermic reactions, while reactions that require heat to keep them going are called endothermic reactions. Equilibrium reactions are both exothermic and endothermic. If an equilibrium reaction requires heat to keep forming products, it will produce heat as the products revert back into reactants. Operators routinely check the temperature indicators associated with a refrigeration system. In most cases, there are temperature indicators for the substance being cooled and for the discharge of the compressor. The condenser in the evaporator may also have temperature indicators located on their inlets and outlets. These indicators can be checked to see if heat transfer is taking place properly. When refrigerant flow through the evaporator is too low, less heat will be removed from the substance being cooled. This will cause the temperature of the substance being cooled to increase.